Welcome back. Today we're doing a deep dive into a technique that's, well, really the engine behind many of the biggest AI models out there. Mixture of experts, or MOE.
That's right. If you're curious about how these giant models like Mixtral or DBRX actually work efficiently, MOE is a key piece of that puzzle.
So it's kind of the essential shortcut to understanding that scale.
Exactly. At its heart, MOE is a clever type of ensemble learning. Think of it like a committee. In fact, they used to call them committee machines back in the
A
day.
committee, okay.
Yeah, where you have several different neural networks, these experts, and they work together. The main goal is to split up a really complex problem into, smaller pieces that each expert can get good at handling.
Okay, right. So let's unpack that a bit. If we were to sort of boil MOE down, what are the absolute must-have ingredients, the core components?
Well, you fundamentally need three main things.
Yeah.
First, obviously, you need the experts themselves. These are the individual networks, each ready to tackle the input.
Okay, multiple experts, got it.
Second, you need some way to actually combine what they all say into one final answer. Usually it's some kind of weighted combination.
Right, makes sense. And the third?
And third, critically, especially for the modern systems, you need the gating network, sometimes called the router. This is the part that decides which experts get to speak, essentially.
Ah, the router. That sounds like where a lot of the magic happens. So
Yeah.
in the older classical MOE, it wasn't really routing, was it? It was more like everyone chips in.
Exactly. Back then, you'd typically calculate a weighted sum based on all the experts' outputs. Every single expert had a say on every single piece of data that came through.
So how did they even know specialization would occur if everyone was involved?
Well, what's really fascinating is looking back at the early research from the 90s, there was this system called the Metapi network.
Metapi?
For what? It was used for phone classification. They were trying to classify sounds from 6 different Japanese speakers. And the system naturally specialized.
Oh, interesting. How so?
Well, you had, I think, 8 experts in total. 5 of them basically dedicated themselves completely to 5 of the speakers. Just one expert per speaker.
Wow. Okay. What about the sixth speaker?
The 6th speaker was handled by a combination, a linear mix of 3 other experts. It wasn't random. The system learned to assign these, local experts all by itself. It showed specialization was possible.
That really sets the stage for the big shift we see with MOE in deep learning today.
Yeah.
Because classical MOE used everyone, it was dense. But modern MOE is all about conditional computation, right?
Precisely. That's the absolute key. We're moving away from using the entire massive model for every calculation. The goal is only activating the necessary parts for a given input.
So less brute force, more selective intelligence.
Exactly. And this is where sparsely gated MOE comes in. Instead of that dense sum of, say, 100 experts, the router uses what's called top crowding. Yeah, it picks the top K experts it thinks are best for the current input token. And K is usually really small, like K1 or K2. The Swiss transformer, for example, often use K2.
Just one or two experts get activated out of potentially hundreds or thousands.
That's the idea. And that's the mechanism allowing these models to have an enormous number of parameters, making them very knowledgeable, without the computational cost becoming completely unmanageable during inference.
And the efficiency gains are pretty staggering, aren't they? I saw a figure in the source material about machine translation.
Oh, yeah, the results can be quite dramatic. MOE models could have, say, 30 times more parameters than a comparable dense model,
30 times.
but actually require less compute time to make a prediction. That efficiency gain through sparsity is, well, it's the reason these huge models are feasible.
But wait, if the router is just picking the top one or two experts, doesn't it risk just picking the same favorites over and over again?
Ah, you've hit on a critical challenge. That's exactly the load balancing problem. If the router constantly favors a few experts, they get overloaded, while others just sit there, unused. You waste all those parameters you trained.
Right, you lose the benefit of having that diverse committee. So how do engineers actually, enforce some fairness, make sure the workload gets spread out?
They typically introduce something called an auxiliary loss function during training.
Auxiliary loss, like a penalty.
Sort of, yeah. You can think of it like a fairness tax. The model gets penalized if it sends too many input tokens to just a few experts and ignores the others. This encourages the router to learn to distribute the work more evenly across all the available experts.
So it's an explicit mechanism to keep the sparsity useful and ensure all the experts are pulling their weight.
Exactly. It maintains the balance needed for efficiency.
So bringing it all together, MOE is fundamentally what enables models like Google's what was it, 1.2 trillion parameters?
Yeah, GLM or Mixtrol 8x7B, Databricks DBRX with 132 billion. These incredibly large models are practical, both financially and technically, largely because of this sparse conditional computation approach.
It's really reshaped the landscape. And before we wrap up with a final thought, just a quick thank you to our sponsor, embersilk.com.
Absolutely. And, while MOE is now pretty standard for large language models, we're seeing it pop up elsewhere too. Vision MOE for images, even in diffusion models for generation tasks.
It's becoming a more general architectural pattern then.
It seems so. And it makes you think, doesn't it? This architecture where you have distributed knowledge and you selectively access only the relevant bits when needed, it kind of mirrors how large organizations, or maybe even our own brains, manage complexity.
That's a fascinating parallel.
So the provocative thought for you, the listener, might be, beyond AI, what other complex systems or fields could benefit from this idea? This notion of assigning specialized, local experts to tackle very specific parts of a bigger problem. Where else could this principle of selective expertise be applied?